Hi, everyone. Good morning. My name is Thomas Parnell from IBM, and today I'm going to be presenting this together with Aleksandr Malyshev from AMD. And we're going to talk about our work to enable vLLM v1 on AMD GPUs with Triton. And I'd just like to say this is joint work between IBM, AMD, and Red Hat. Okay, so just to give you an overview of what we're going to talk about today, we'll start by explaining the title. What is vLLM v1? Why did we need to build a new attention backend for it? And why do we use Triton for that? Then I'm going to get into some basic terminology, which will help to understand when we present the details of these kernels. And I'll talk about the baseline that we used as the starting point for this work. Then we're going to go pretty deep into how we optimize these kernels, what worked, what didn't, and we'll close by showing you some very recent performance benchmarks comparing vLLM v1 against v0 on MI300X GPUs. Cool. So let's get into it. What is vLLM v1? So this goes back to, I think, January this year, where the vLLM team announced a complete redesign of vLLM's internal architecture. So from the outside, for users, nothing changes, it's identical, but the internals changed a lot. So why did we do this? I think the goals of v1 were threefold. One is to make the vLLM code much more simple, like v0 had become a bit of a mess. To make vLLM easier to extend and plug custom behavior in. And most importantly, to make vLLM more performant. So in v0, we had lots of different optimizations like chunked prefill, spec decode, and many more. But these optimizations didn't necessarily work together. In v1, we want to make these optimizations work together seamlessly and enable them by default. Since then, that was in January, v1 now has many more features related to performance, like zero overhead, automatic prefix caching, integration with Torch Compile, which we heard about yesterday, and stuff like PD disaggregation, and many more. So v1 is awesome. We want it. So the next question is, why couldn't we just take the attention kernels we used for v0 and run them on v1? So there's a bunch of reasons. The first is that v1 requires the attention kernels to support all these different optimizations, like chunked prefill, prefix caching, spec decode. But also, it's important to understand that v1 changed the way that we batch together requests in vLLM. So in v0, we always distinguish between a prefill batch, where we have a collection of prompts which are all prefill requests, and a decode batch where all of the sequences in the batch are in the decoding phase. So in v1, a batch can comprise both, and other cases, which I'll talk about later. So a batch contains lots of heterogeneous requests in different states, and that batch also doesn't enforce any order. So sometimes you get the decodes in the beginning and then prefills, but that isn't guaranteed. So why did we use Triton? So when v1 was first released in its alpha in January, the only attention backend that really supported all of these use cases I described just on the previous slide was flash attention, and in particular the CUDA variant of flash attention. So of course that implies that v1 was only supported on NVIDIA GPUs. So how could we get this working on AMD? I mean, one option is to say, let's take the v0 backend and port it to v1. But that v0 backend used a lot of custom HIP kernels, which I don't know how to write that. That makes it, it takes more time to adapt those kernels to this v1 use case. So the team across IBM, AMD, and Red Hat decided to try and build an attention backend for v1 using Triton. So why? Why Triton? Triton is super easy to be productive, right? You can write the kernels quickly, prototype them, benchmark them. They're also flexible, so when new models come out, you can adapt those kernels if necessary. And the Triton kernels are also portable across different platforms. And my colleague Burkhard is going to talk more on that topic later in this session today. So before we get into the guts of the kernels, I just want to introduce some basic terminology that I think is needed to understand them. So there's three important quantities to understand: the context length, the query length, and the sequence length. So the context length is like the number of old tokens. This is like the number of tokens in previous forward passes that you've already computed the KV tensors for and stored them in your paged KV cache. The query length is the number of new tokens, like the number of tokens in your current forward pass that you want to compute the KVs for and append them to the old tokens. And the sequence length is the sum of both of those. So just to help understand, you can think of some like corner cases of this thing, right? So if the context length is 0, so you only have new tokens, this corresponds to your standard prefill operation, where you're just prefilling the whole prompt. If the context length is non-zero, so you already have some paged KV cache that you've computed in previous iterations, but your query length is like 1K, 2K, 4K, this is what we see when we do chunked prefill or prefix caching type ops. In the lower left, you see a decode. So that's, again, a very well-known op where we have like the query length is 1, and we have a lot of context that we've built up from previous iterations. And finally, spec decode looks a lot like decode, except that query length is not 1. It might be 3 or 4 tokens, something like that. Okay, so now getting into like the baseline. So this was like, how do we just bring up vLLM v1 on AMD GPUs as quickly as possible? So actually, this was kind of easy. So we had an existing kernel that came from this light LLM project called prefix prefill. So this kernel supported all of the stuff I just described. So it can support all of those 4 cases and everything in between. So this was a super cool way to get started. But we found the performance was really bad, right? So it was actually 6 times slower than v0, which like defeats the whole purpose of v1. So we got to fix that. So in order to fix it, we first had to understand like what the problem was, right? So this slide is a bit complicated, but I'm going to walk you through it. So this figure shows like what one of the programs of prefix prefill is really doing. So when we launch this Triton kernel, you specify a grid, right? And that's shown in the bottom here. So it's a 3D grid of batch size, number of query heads, and then query length divided by a block size, block M. So what this means is we're going to like parallelize all of the work across these 3 dimensions, right? So each program is completely independent, doing its own work. And what you see in this figure is what that program does. And I don't show the first 2 dimensions here. I only show the query length in the vertical axis. And then the horizontal axis is like the sequence length. And this is the dimension along which the kernel does like the online softmax algorithm. So it's basically the same algorithm from the Flash Attention 2 paper, where you iterate tile by tile along the sequence length and compute online softmax. So that each box you see here is 1 tile, like I0, I1, it's just a for loop, basically. So what you can see here is that we have 2 different block sizes. The block M runs in the query length dimension, and it's set to 128. And the block N runs in the sequence length dimension, and it's set to 64. So what's wrong with this? Why doesn't it work? So for decodes, the query length is 1, right? So, but we've hard-coded this block M to be 128 tokens. So that means for decode sequences, each program and every tile is doing like 100x more work than it really needs to do. So you will look at this and say, that's dumb. Like, why don't we just tune block M? Why don't we make it smaller? Why don't we set it to 1 even? But of course, doing that will ruin the performance for the other sequences. So we need to launch the kernel for like the whole batch, right? Which is a heterogeneous batch containing prefills and decodes. Setting block M to 1 might work well for decodes, but it's going to mess up the performance for prefills, right? So the kind of zeroth order solution we came up with here was to split this. So we launched prefix prefill. And for sequences with query length 1, we just terminate it early. So those programs stop. And then we launch a second kernel to process the decode sequences. And that's what I will describe on this slide. So on this slide, I show the kernel that we use for decodes. I'll start on the left here. So let's see how the launch grid changed, right? So on the previous slide, I showed a 3D launch grid. This launch grid is only 2D. It has batch size, number of query heads, and the query length dimension is gone. That's because it's just 1, right? So we can collapse it down. And what I show in the figure, on like the vertical axis, we have the number of query heads, and on the horizontal axis is the context length. And again, we're just doing tile, softmax, tile by I1, I0, I1, sorry, like along the horizontal axes. So the difference here is that the tile size in the context length dimension is 16. That's aligned with the default attention block size in vLLM. And in the vertical dimension, the block size in the query heads is 1. So each tile processes 1 query head. This worked great for models like Llama 2, which don't use GQA, grouped query attention. But of course, all of the new models do use that. That's what we show in the figure on the right. So in order to get like the best performance here, we needed to introduce a new tiling in the vertical dimensions, in the query head dimension. And we changed the launch grid. So we only launched this kernel for batch size times number of KV heads. So each program for a KV head will read the data for that KV head and process like all of the query heads which share it. And that's why you see this new block size in that vertical dimension. So this improves the performance because you have less data to move, but it also improves the performance because we can do a trick where we pad up that tile size in the query head dimension to 16, which forces Triton to use the matrix cores on the GPU. And we see a big boost in performance from doing that. So with all of these optimizations for like GQA-based models, we now see that we're 4.7 times faster than the baseline prefix prefill kernel. At this point, I'm going to hand over to Aleksandr.
Yeah, thank you for a great introduction and basically sharing the problem statement for the attention kernel that needs to handle both decode sequences and prefill sequences in the same batch, and complexity in basically developing one kernel for everything. However, I wanted to just to step back slightly into what we started in AMD in parallel to, with the IBM research. So we took that prefix prefill and basically the kernel right from the way it used to be, was assuming lots of, how to say it, easy steps to do really nice optimizations at first. So for instance, as the first step, for the kernel, when you run a benchmark, you basically generate a when you run the Triton compiler and see what the assembly goes out and what the splitting rate is. Originally, it was using like 8 warps per compute unit, which assumed that it will be 2 warps per SMD because every compute unit has 4 SIMT or streaming multiprocessor if you are talking about NVIDIA. And as more warps we have, as more number of vector registers needs to be split on. So for instance, in this case, when we have 2 warps per SMT, so 512 vector register needs to be split. And that is why not most of the time for that particular case, it wasn't enough. And it was a really high splitting rate. And it was a killer for the kernel performance. So the first and easy step was like to reduce a number of warps from 8 to 4 and basically give every warp to use all 512 vector registers, which kind of increased the performance by 2 or 3x, and it was really great to start with. So it kind of unblocked lots of experiments to go with the AMD hardware. So the second step was when we reduced the number of warps, then it became 1 warp per SMT, so the parallelization wasn't great. And the kernel was I started refactoring for the kernel basically to provide more parameters for the after tuning, and that was the goal, is to reduce the amount of memory the kernel, every instance of the kernel needs to handle, in order to increase warp parallelization back to 8. That's the second step, and the third step is the it was from the looking from the assembly. So there are different ways to access memory on GPUs. It might be single element access, or it might be vectorized access, and And when kernel has the vectorized access to memory, basically the load is the most efficient one. However, for Triton kernel to figure out if it allowed to do a vectorization for the load, it's not easy, and that is why it requires to generate blocks of offset as how to say it, as more clear as possible using all the constant variables, right? So with so they know in compile time. So that was the third step. Basically, is to instead of loading context from the several KV cache blocks, right? And not aligned for the block size, it was refactored to access only one KV cache block, right? Because vLLM is a block structure for KV cache. And once the alignment was organized, then it opened a way to do a loop unrolling, because every loop was like independent and every loop was working with just one KV cache block. And as long as the KV cache is not huge, right, then several loops might be unrolled into one kernel. Then again, refactored online softmax. For some reason, it was implemented in the way it's done on paper, but there were ways to reduce a number of computations, and as it happened in the hot loops, it was a really nice first improvement that reduced the amount of vector registers needed and compute as well. And, the last step is also pretty obvious. When we do load or store in the loops, right, most of the iterations we don't need to check for the edge cases, right? This needs to be checked on the when the iterations gets to a bound. Basically, once you remove it, you'll get a performance. Then in AMD we thought that, hey, from V0 we have really nice and optimized kernel for the decode, and basically that decode kernel implements flash decode attention, which parallelizes the context onto blocks and then do a reduction. It was very reasonable to took that kernel from V0, refactor it, and adapt it to V1 needs so that it can handle only decode sequences in the batch, while the Triton kernel will handle chunked prefill or speculative decoding sequences from that kernel. Basically, that happened, and it gave another performance boost, right, which gets us closer to the goal, is to get more or less on par with the NVIDIA attention that was used for vLLM that time. And on the slide, you see lots of tunes that you can find in that kernel, and as well as a link. It's implemented in C++. While the kernel is great, it's again has lots of tricks, and even for the person knowing C++, it's not very easy to understand. It takes a while, and then to extend it to a new features like window, sliding window, like alibi to implement there, or syncs, the recent one in GPT-OSS, right? That is why, and also it's not very easy to port into a new architecture. For instance, recently we, how to say it, in AMD switched from MI300 to MI350, slightly different accelerator with lots of new nice features. That was the problem. And that is why IBM and then AMD picked up an idea to do a development for a unified attention kernel, which basically gets all the ideas all together. And right now we have, I don't have much time, so I need to skip a couple of this. Right now we have 2D, 3D attention kernels, and the idea is that 2D is mostly used for prefill heavy kernels, and 3D for decode-heavy kernels. They have different characteristics, have different optimizations for it, depending on the prefill or decode use, right? For instance, for decode use, we don't need to use cache, at least L1. SVA is applicable only for prefill, right? Because for decode kernel 3D, there is not enough parallelization for it, and so on and so on. Yeah, I'll speed up a little bit. And we are completing our presentation by a benchmark that we did. We tried to compare what V0 with the V1 we currently have. Unfortunately, V0 nice support stopped somewhere in summer, long time ago. V1 is the main line for now, right? And we tried to do as honest as possible, right? Because V0, as Thomas said, there was no by default chunked prefill, and the number of sequences in the batch was also different and whatnot, right? And we took a Mistral 24 billion, basically provided the commands here if you want to reproduce it. And in the end, we we see that around 10% we get better time to first token, inter-token, and the throughput in general if you compare V1 with V0. On top of that, just want to repeat what Thomas said originally. With the V1, we are getting into PyTorch ecosystem with the torch compile, with all the passes of torch compile. We are getting CUDA graph out-of-box support, and more really nice features that either developed or soon will be developed. I'm done. Thank you. Questions?
Any questions?
Questions? If not now, feel free to come to us and basically ask later. Thank you for your time.
Thank you.